How the Romans drained mines without electricity. The Romans had a problem. Actually, they had a lot of problems. They built roads across continents, aqueducts across valleys, concrete domes, massive harbors. But some of their hardest engineering battles happened underground. In the dark, inside mines. Because the Romans wanted metals. Gold, silver, copper, iron. Their empire needed them for coins, weapons, tools, plumbing, construction, and trade. And the deeper they mined, the richer some of those veins could become. But the deeper they went, the more the earth pushed back. Rock collapsed. Air became harder to breathe. The tunnels grew hotter. And worst of all, water kept getting in. That sounds like a simple inconvenience. It wasn't. Water could end a mine. Imagine digging a shaft deep into the ground. You follow a promising vein of ore. Every meter takes effort. Workers cut the rock, carry material out, support the tunnel, push farther down. And then water starts seeping through the walls. Maybe slowly at first. Just a trickle. Then a puddle. Then a pool. Then the lower passage is flooded. And suddenly the richest part of the mine is unreachable. This was one of the greatest limits on ancient mining. Not the ore. Not the tools. Water. And that raises the question. How do you drain a mine? Without electricity? No electric pumps. No diesel engines. No steel pipelines. No modern machinery. Just wood, metal, human labor. And a problem that keeps refilling itself. The Romans did not solve that problem with one miracle machine. They solved it with systems. And one of their most impressive solutions involved something surprisingly simple. A wheel. At first, that may not sound very impressive. A wheel? That's it? But this was not an ordinary wheel. It was part of a water-lifting system designed to fight one of the most stubborn enemies in mining. Before we get to the machine itself, it helps to understand the scale of the challenge. In many mines, water entered from seepage underground. It could collect in low areas, shafts, and deeper galleries. And once enough water built up, work could slow down or stop entirely. So the Romans had to think like engineers. First question: can we stop the water from entering? Sometimes not really. Second question: can we guide some of it away? This is why drainage adits mattered. An adit is a horizontal passage driven into the side of a hill or mountain. If you build it carefully, water can flow outward by gravity. That already helps. In some Roman mining areas, channels were also cut to help move water away from working zones. But gravity alone had limits. Because the deepest parts of a mine are, by definition, below other parts of the mine. And once water collected at a low point, you had to lift it. That is where the Romans moved from simple drainage to mechanical drainage. And for the shallowest or simplest situations, you could imagine fairly direct methods. Buckets. Oops. Human labor. But once a mine got deeper, that approach became painfully inefficient. Lifting bucket after bucket by hand from a deep shaft is slow, exhausting, and not ideal when water keeps returning. So the Romans needed something better. And that something better is described by the Roman engineer Vitruvius. In Book 10 of On Architecture, he explains different machines for raising water. One design uses a wheel fitted with containers around its edge. As the wheel turns, those containers fill below, rise upward, and empty into a channel above. He also describes chain systems with buckets for lifting water higher. That description matters because it shows this was not fantasy. Romans understood water lifting machinery in detail. But even more important than the text, we have the archaeology. At Dolaucothi, the Roman gold mine in Wales, miners in the 1930s discovered Roman workings that included a wooden water drainage wheel. That alone is exciting. It means these machines were not just described in books. They were actually used underground. And then there is Rio Tinto in Spain. This is where the story becomes extraordinary. Archaeological finds from the Roman mines there include parts of water-lifting wheels, and records of discoveries indicate roughly 30 such wheels were found, including a famous system of 16 wheels arranged in pairs across 8 levels. Together, those wheels could lift water a very large vertical distance. Not with one giant pump, but step by step, level by level. And that is the genius of the Roman solution. One will does not need to raise water all the way to the surface. It only has to raise it to the next stage. Then another will takes over. Then another. Then another. Instead of trying to win the whole battle at once, they broke the problem into smaller battles. That is real engineering. So how would it actually work? Picture a deep mine with a flooded lower section. At the bottom, water collects in a sump or low basin. A worker steps into or operates a large wooden wheel. As the wheel turns, compartments or buckets around it dip into the water. They fill. Then they rise. At the top, the water spills into a wooden trough or channel. That trough carries the water to a slightly higher collecting point. Now the water is no longer at the lowest level, but it is still underground. So another wheel, positioned above, repeats the process. Then another. And another. What you end up with is not one machine, but a vertical chain of machines. A relay race against groundwater. Each wheel doing one part of the job. And all of them depending on timing, labor, carpentry, planning, and space. Think about what that means. First, someone had to design the system. Not just the wheel itself, but its diameter, placement, support, and relationship to the next level. Second, the components had to be made. These were large wooden constructions. At least one Roman wheel from Rio Tinto, preserved in part, is about 4.6 meters in diameter. That is huge for a machine operating underground. Third, the parts had to be transported and assembled. Not in a sunny workshop. Inside a mine. In cramped, damp, dark conditions. Fourth, people had to operate the system continuously enough to keep the mine usable. This was not a one-time fix. It was a constant fight. And that changes how we should imagine Roman mining. We often picture ancient mining as crude. Men with hammers in dark holes. Brutal. But crude? Not always. At least in some major operations, Roman mining was organized, technical, and deeply engineered. Water management was not an extra detail. It was central. Without drainage, deeper mining becomes impossible. So every successful deep mine was, in part, a triumph of hydraulic thinking. And the Romans were good at hydraulic thinking. We usually remember that through aqueducts. Water coming in. But mines show the opposite challenge. Water going out. And both required the same core skill. Understanding how water behaves. Where it flows. Where it collects. How gravity helps. And where gravity stops helping. That last part is important. Gravity could help drain water outward through adits if the terrain allowed it. But once water sat below the level of safe discharge, the Romans had to spend energy to raise it. And because they had no electricity, that energy came from people. Human power turned the wheel. The wheel lifted the water. The channel moved it onward. Then the next wheel repeated the process. Simple idea. Demanding execution. There is also something almost modern about the logic. Today, engineers often solve difficult problems by dividing them into stages. The Romans did something similar. Not because they had advanced mathematics or computer simulations in the way we think of them today, but because they understood systems. One wheel is limited. A chain of wheels is scalable. That difference matters. And it explains why the finds at Rio Tinto are so powerful. 16 wheels across 8 levels means planning, standardization, coordination, an organized response to a recurring industrial problem. And when we combine that with Vitruvius, we get a fuller picture. Text and archaeology start talking to each other. The engineer describes water-raising machines. The mines show us that such machines were not theoretical. They were built, used, worn down, left behind underground. That is one of the most satisfying things in ancient engineering. When an idea survives in writing, and also in wood and metal. So, did the Romans completely defeat water in their mines? Not permanently. No ancient drainage system worked forever. It required maintenance, labor, and continued organization. And if the work stopped, water could reclaim the lower levels. In a way, that makes the achievement more impressive, not less. because it reminds us that this was never a magical invention that solved everything forever. It was an ongoing contest. As long as the mine was worth working, the system had to keep working too. And maybe that is the most fascinating part of the whole story. The Romans did not drain mines without electricity by inventing one impossible machine. They did it by combining observation, mechanics, labor, and systems thinking. They used gravity where gravity helped. They used tunnels where tunnels helped. And where neither was enough, they built machines to lift water upward, one level at a time. So the next time you hear about Roman engineering, don't think only of roads or aqueducts. Think underground. Think of timber wheels turning in the dark. Think of miners standing in wet passages, fighting a battle against rising water. Think of a machine lifting bucket after bucket toward the light. Because long before electric pumps, the Romans had already found a way to dig deeper, not by ignoring the problem of water, but by understanding it well enough to move it out of the way.